Hi everyone. Today let's continue with sessions 5.5. We are not skipping 5.4. We will first cover 5.5 and then we'll go back and cover 5.4. So do you remember what we have been learning over this chapter? So we have been learning how to solve differential equations, higher order but linear homogeneous differential equations. Homogeneous means the right hand side of the differential equation is 0. Okay, so today we're gonna talk about what happened with non-homogeneous equations. So that means if the right hand side is a function of x, it's not 0. Okay, so with our shorthand notation, we can think about L as the operator. So L is like, in this problem, we're taking the second derivative and plus p of x. We take the first derivative plus q of x. Okay, and when you apply the linear operator to y, then you just put, like, have this guy apply to y. So that's why you have the second derivative of y, and we have the first derivative of y plus q of x times y. Okay, everybody? So this is a shorthand notation. Well, we talk about that for linear ODE, we have general solution. And the general solution is the sum of a homogeneous solution and a particular solution. So homogeneous solution is the solution of the homogeneous. So this is solution of the homogeneous differential equation. Okay, so particular solution will take care of what happens if we have the right hand side, the force function f of x is not 0. Okay, so let's recall what we learned before. So given, for example, given a second order linear ODE with constant coefficients, we first look at the characteristic equation. Okay, so in this case, we have like AR squared plus BR plus C equal to 0. Okay, and then we solve for R. Alright, so if the R is a real numbers, okay, so if the R is real number, then we expect the solutions will contain e to the x, right? It will contain this term. If R is complex, well, then we know the solution, for example, is alpha plus minus beta I. Then the solution contains e to the alpha plus beta I times x. But because we're given real coefficients, that we should expect to have real solutions. So instead of writing that, the solution will contain e to the alpha x cosine beta x and some terms of e to the alpha x sine of beta x. Okay, and what happens if R is repeated? So repeated means it could be a real solution or it can be a complex solution. So if it's repeated, let's say the multiplicity of R is k, okay, then the solutions will contain, you start with the original, let's say if you have like a real, so you have the original and you multiply by the number of x until you reach the multiplicity. Okay, so actually it's the multiplicity minus 1 e to the rx. Okay, so this is when R is real, okay? So if R is real, if R is complex, then you get the original term e to the alpha x cosine beta x, and you keep multiplying by it. So x e to the alpha x cosine beta x until you reach the multiplicity minus 1. Okay, so k minus 1 e to the alpha x cosine beta x. And same thing with the sign, because the complex roots always appear as pairs. So you also have the sine and cosine there together, okay? You see them both. Okay, so that's why if you see the solution, you have an idea about, okay, what's the roots, what's the corresponding roots in the characteristic equation, and what's the multiplicity of that root. Okay, all right. So today, for solving non-homogeneous equation, so today we will look at the method so-called undetermined coefficients. Okay, so we have some restriction about this method. Part A, first, the homogeneous problem must have constant coefficients. Okay, so it's a linear ODE with constant coefficients. Second, the force function, the right-hand side on the equation, must be a special form. It's either a polynomial of degree greater than or equal to 0. Okay, so okay, so you can think of, polynomial is like it corresponds to r equal to 0, right? Because if r equal to 0, what's the solution? What solution looks like e to the 0x, and that is e to the 0, which is 1. Okay, and if the root is repeated, if the root is repeated, then your root is like so say multiplicity is k, then your solutions will contain the terms 1x, x squared, x to the k minus 1, right? So so that's why polynomial of degree greater equal to 0 corresponds to like the root 0 in the characteristic equation. Okay, real exponential or complex exponential. So real exponential is like e to the alpha x, and e to the rx. R is real, so it corresponds to r, the roots is real. Complex exponential, such as sine and cosine. So if you have like e to the alpha x sine beta x, or e to the alpha x cosine beta x, they correspond to alpha plus or minus beta I. And then it could be sum or products of the above. So what it means is the solution you expect to see when you solve the homogeneous equations. So for the non-homogeneous one, if we want to use the method of undetermined coefficients, your right-hand side should be of the same type of those forms, such as polynomial, real exponential, or complex exponential, like contains the sine and cosine, or sum or products of the above. Okay, for other form, we actually have another method. It's called variation parameter. So variation parameter can solve it's a more general method for linear equations, but we are not going to cover in our course. Okay, but if you're interested to know, I'm happy to share with you. Okay, just talk to me and then I can share this method, variation of parameter. It works in general. So the right hand side f of x is not restricted to those forms. Okay. All right. So technique. Okay, so what are the steps? The steps of how to solve a non-homogeneous ODE is we first find the homogeneous solution. Okay, and second, we want to find a particular solution. So to find particular solution, we can try a solution with the same form as f of x. If it does not work, multiply an appropriate power of x. Okay, I will explain that more later when we go over examples. Okay, so let's look at examples. Example 1. Find the general solution of this non-homogeneous differential equation. Okay, so let me get my black. Okay, so the first step, we want to compute the homogeneous differential equation. So that is, we compute the differential equation with the right-hand side is 0. Okay, this is the first step. And then what is the characteristic equation? Well, this is r squared, this is 2r, this is 3. How can we factor it? Oh, you may realize we actually cannot factor it. Okay, so because b squared 4 minus 4ac, which is 12, is negative. So that's why we're not able to factor it. We expect to see 2 complex roots. So the quadratic formula, 2a is 2, negative b plus or minus b squared minus 4ac. So that is negative 2 plus or minus 4 minus 12 is negative 8. So that's 2 root 2i. Okay, so with split, we get minus 1 plus or minus root 2i. So this is our complex roots, okay? And because it's complex, we expect our solution is gonna be like C1. This is the real part. This is the imaginary part. So real part is like alpha e to the alpha x or minus x times cosine beta, so square root of 2x plus c2 e to the minus x sine of beta x. Okay, everybody? So this is our homogeneous solution. This is part 1. Okay, so part 2. How do we find the particular solution? Well, look at the right-hand side. In this case, it's e to the 3x. Okay? What does this guy correspond to? So, we know polynomial, it corresponds to the root 0. And so this is real exponential. So it corresponds to the roots is 3. Okay? And then you can see, well, here it corresponds to the root 3, and then the solution corresponds to root 3 will look like a e to the 3x. So here we want to use a because we want to distinguish the constants of the homogeneous solution. For the homogeneous solution, we name the constants C1, C2, C3, C4. For the particular solution, we use A, B, C, D. Okay, everybody? Alright, so that's why when we set up the general form of the particular solution, depending on e to the 3x, our general form should look like a times e to the 3x. So let's work it out and see what happened. Okay. So let's differentiate. Okay, so this is our our solution of this form. So we're gonna differentiate again to plug in our ODE and then find a constant a. Okay, so that's why we need y prime. Y prime is 3a e to the 3x. Y prime prime is when you take another derivative, you get 9a e to the 3x. So far, so good, everybody? Alright, so let's plug it in. So we plug in, we get, so here y prime prime, which is 9a e to the 3x plus 2y prime times 3a e to the 3x plus 3y. So y is a e to the 3x equals to e to the 3x. Okay, can you see they all contain the factor e to the 3x. Let's combine them. So let's look at the constants. The constants 9a, 6a, 3a. So 9a plus 6a plus 3a equals to 1. So that is 18a equals to 1. A is 1 over 18. Oh, so now we can write our particular solution is 1 over 18 e to the 3x. So for particular solution, you can actually solve the constants, okay? So our general solution, okay? The general solution equals to homogeneous solution plus the particular solution. So that is c1 e to the minus x cosine square root of x plus c2 e to the minus x sine square root of x plus 1 over 18 e to the 3x. Okay, so that is that's our general solution. So if the problem gives us initial condition, then after this step, you're going to plug in the initial condition and solve C1 and C2. Okay, so let me write it down. Okay, so if the problem gives initial condition, we can then plug in the initial condition to find C1 and C2. So after this step, okay? All right, so that is example 1. Okay, let's continue. Oh, so we're actually here. So for example, if our initial condition, we have y of 0 is 0, y prime of 0 is 1, how do we find the C1 and C2? Okay, so that is our general solution. Let's write it down here. Okay, so y of 0 is 0. Y of 0 is, we plug in x is 0, so C1 e to the 0 is 1, cosine 0 is 1, so that we just have C1. And then C2 times e to the 0 is 1, sine 0 is 0, and then plus, when we plug in 0, we get 1 over 18. E to the 0 is 1. So what do we get? This is gone, so we have C1 is minus 1 over 18. Okay, everybody? And then we take the derivative. Okay, so y prime is, oh, okay, so let me put y here because I want to show you here when we differentiate, we actually need the product rule. Okay, so C2 e to the minus, oops, did I press something wrong? Okay, so oops, sine square root of 2x plus 1 over 18 e to the 3x. So when we differentiate, this is a product, so that's the derivative of the first guy, which is minus c1 e to the minus x times the second guy plus the first guy times the derivative of the second guy, which is negative sine square root of 2x, but u prime, which is square root of 2, plus here we have another product rule. The derivative of the first guy is negative c2 e to the minus x sine square root 2x, and then plus the derivative of the second guy, which is cosine square root 2x times square root of 2, plus when we differentiate, we multiply by 3. 1 over 18 times 3 is 1 over 6 e to the 3x. Okay, so let's plug in y prime of 0 is 1. So when we plug in 0, the first term, e to the 0 is 0, cosine 0 is, e to the 0 is 1, cosine 0 is 1, so we have minus c1. The second term, you see the sine of 0 is 0, so the second term is gone. And the third term, okay, let me use color here. So the second term is gone. The third term, you see the sine, so it's also gone. And then the fourth term we have the cosine. So cosine 0 is 1, so we have this is square root of 2 c2, and then the last term we have 1 over 6. Okay, so how do we solve for c2? Well, square root of c2 is 1 minus 1 over 6 plus c1, but c1 is negative 1 over 18, so 18 is the common denominator. Then we have 18 minus 3 minus 1, which is 14. So 14 over 18, that's 7 over 9. Okay, so c2 is 7 over 9, and we divide it by square root of 2. Okay, so we get our solution. Y of x is c1. c1 is negative 1 over 18 e to the minus x cosine square root of 2x plus c2, 7 over 9 square root of x e to the negative x sine square root of 2x plus 1 over 18 e to the 3x. So this is our final answer. Okay? So to find, when you want to find a constant c1, c2, you have to get the general solution first. Okay, so if you just use the YH, the homogeneous solution, and find a C1 and C2, that will be wrong. Okay, you can see the particular solution plays a role here and there. So don't forget, you have to get the particular solution, and then you can write the general solution as the sum of the homogeneous solution and the particular solution. Then you can plug in the initial value there to find a constant C1 and C2. Okay, so let's continue. Yeah, you can see the problem is getting longer. Yes, and right now we're only doing second order, so later on we'll do higher order later on of today. Okay, so it's okay, so let's continue. So example 2, the first step, we compute the homogeneous differential equation. The homogeneous differential equation is, we have the left hand side equals to 0, right? And then what is the characteristic equation? The characteristic equation is, okay, you can try to pause the video here and work on it, okay? And after you're done, we can check our answer together. So we have r squared minus 2r plus 1 is 0, right? And we can factor it. So we factor it. Oh, notice that this is a complete square. So this is r minus 1 squared equal to 0. So we have r equals to 1. And it's repeated. So the multiplicity is 2. What is YH? What's the homogeneous solution? Well, the homogeneous solution is then C1 e to the 1 times x, which is x. Multiplicity 2. Multiplicity 2 means you for the next term, you just multiply by extra x. See, you keep going until you reach the x to the multiplicity minus 1, in this case, just 1. Okay? And you can also count this by, this is 2, so degrees of freedom is also 2, so you see there is 2 degrees of freedom. Okay? So multiplicity k, you have degrees of freedom k, so you should have k constant there. Alright, so that is the first step. And then let's continue, okay? So for yp, to find yp, we'll look at the right hand side. The right hand side is 5 cosine 2x. Well, cosine 2x, what's the root it corresponds to? Well, it corresponds to the alpha is 0 and the beta is 2. Do you agree? Okay, because then it's e to the alpha x cosine beta x and e to the alpha x sine beta x. Beta is 2. And so it corresponds to the root. The root is plus or minus 2i. So far, so good, everybody? So this root r equals plus or minus 2i. What is the general term for it? How do we set it up? The general term for plus or minus 2i is a e to the 0 and cosine 2x plus b e to the 0 times sine 2x. Right? So this is the general form, corresponds to the root plus or minus 2i. Okay? And so this is our setup. And then let's continue. So we're gonna take the derivative and the second derivative and then plug into the differential equation to find our constants a and b. Okay? So let's see here. Yp prime is derivative of cosine is minus sine, and there's an extra 2 because of the chain rule. And derivative of sine is cosine, and there's extra 2 because of the chain rule. Okay, how about second derivative? Derivative of sine is cosine, there's extra 2 because of the chain rule. Derivative of cosine is minus sine, and there's extra 2 because of the chain rule. So far, so good, everybody? Okay. So let's plug this into our differential equation. Y prime prime, which is minus 4a cosine 2x minus 4b sine 2x. Minus 2 times y prime. Y prime is negative 2a sine 2x plus 2b cosine 2x. So don't forget your parentheses. Your parentheses is so important. Okay? Yes. Especially when the problems get more and more complicated, you have to be careful, catch your breath, and work on it. Okay? So plus y. Y is a cosine 2x and b sine 2x equals to my right hand side, which is 5 cosine 2x. Okay, so far so good, everybody? Alright, so let's get rid of the parentheses. Let's distribute it. So this is negative 4a cosine 2x minus 4b sine 2x. 2 times 2, 4. Negative, negative, positive. 4a sine 2x. Negative, 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 positive, so negative. 4b cosine 2x. A cosine 2x. B sine 2x equals to 5 cosine 2x. Okay, so now let's compare the like terms. So let's look at the cosine 2x. What are the coefficients of cosine 2x? Well, we have minus 4a, right? Let me use a line to denote. And minus 4b, and the a, and on the right hand side, that's the 5, right? Okay, so let's simplify it. We get minus 3a minus 4b equals to 5. So far, so good, everybody? And then, so here, what are we doing? We compare the like terms. Okay, and then next, let's compare with the coefficients of sine 2x. So we have this guy, minus 4b, and this guy, 4a, and this guy, b, equals to, there's no sine 2x on the right. So that's 0. So we have 4a minus 3b equals to 0. Okay, so you can use, here we get 2 equations, 2 unknowns. We should be able to solve it, right? And let's solve it. Because this is just a 2 variable, 2 equation. I can solve it easily. I don't need to use a matrix. But if you get more variables, more equations, I strongly recommend you to use the matrix to solve. So here I simply do, oops. Okay. So we want to eliminate one of the variable, right? How do we eliminate? We multiply the first equation by 4, then we have minus 12a minus 16b equals to 20. We multiply by the second equation by 3, so we have 12a minus 9b equals to 0. Then let's call this is equation 3 and equation 4. So we can add them together. Then a is cancelled. We have negative 25b is 20. So b is negative 20 over 25. 5 is a common factor, so that is negative 4/5. That's b. And how to find a? I can then plug in equation 2. Well, equation 2, we have, let's see, 4a is then 3b, which is negative 12 over 5. And then a, both sides divided by 4, so negative 3 over 5. So far, so good, everybody? Okay, so finally, our general solution is, the homogeneous solution, which is c1 e to the x plus c2 x e to the x. Plus the particular solution. What the particular solution is a cosine 2x plus b sine 2x. But a is negative 3 over 5 cosine 2x. B is negative 4/5 sine 2x. So this is our solution of the problem. Okay, so the steps very similar as before. First, we compute, we look at the homogeneous solution, corresponding homogeneous solution. We find the homogeneous, we look at the homogeneous differential equation and find the homogeneous solution. And then we look at the right-hand side, look at the f of x parts to set up the particular solution. And then we just differentiate the particular solution and then plug in it and find the constants a and b. Then we can get it. All right. Let's continue. Find the general solution of this guy. So follow the same steps. Look at the homogeneous differential equation. And then this corresponds to the characteristic equation. So y prime prime is r squared 2r plus 3 equal to 0. Okay, so can we factor it? Well, let's see. So here we cannot factor it. All right, so we use quadratic formula, so it's 2a negative b plus or minus b squared, which is 4 minus 4ac. So we get, here we have negative 2 plus or minus, this is square root of negative 8. So 8 is 2 root 2 I over 2. So this is minus 1 plus or minus square root 2i. Okay, then because it's a complex root, the homogeneous solution is going to be C1 e to the minus x cosine square root of 2x plus C2 e to the minus x sine square root of 2x, right? So this is a homogeneous solution. Okay, for particular solution, well, you look at the right-hand side. The right-hand side, this guy, corresponds to r equal to 0, right? Yeah, so polynomials all corresponds to r to the r equals to 0, because then e to the 0x is like constant. So that's why you have, if it's repeated, then you, okay, for repeated, you can have 1x, x squared. If, say, the multiplicity is k, then you're gonna expect x to the k minus 1. So far, so good, everybody? So here, what's the highest power? Well, the highest power is x cubed. So x cubed, that corresponds to the multiplicity is it 3? No, the k minus 1 is 3. So the multiplicity is actually 4. Okay, then what is the setup for our root 0 with multiplicity 4? So our general setup is a, okay, that's the first term, like corresponds to 1, and then bx plus cx squared plus dx to the 4. No, not x to the 4, it's x cubed, because it's multiplicity 4, so that's why it's x to the multiplicity minus 1, which is 3. And you can see, here, even though the right-hand side does not contain square or 1, but when you set up the yp, you're going to set up a general form, so you also need to include, the highest term and the lower terms, because you're going to see those lower terms when you differentiate. Okay, so if you only set up this, if you only set it up like this, when you differentiate, you're gonna expect to see x squared and x when you take the second derivative, right? So only this term is not enough. You need a general term. Okay, what the general term contains all the possibilities. Okay, so this is our setup of the particular solution. Let's continue and differentiate it. So yp prime is then derivative of a is 0. Then we have b plus 2cx plus 3dx squared. That is yp prime. Okay, let's continue. How about yp prime prime? Well, that's derivative of b is 0, and then we have 2c, and then we have 3 times 2, 6dx. So far, so good, everybody? Okay, let's see. Let's plug into our differential equation. It's y double prime, so 2c plus 6dx. Plus 2 times y prime. Y prime is b plus 2cx plus 3dx squared plus 3y. Y is a plus bx plus cx squared plus dx cubed. That equals to right-hand side x cubed plus 3x. Okay, let's multiply out. So 2c 60x. Here we have 2b 4cx 6cx squared. And distribute the 3a 3bx. 3 times cx squared is 3cx squared. And 3d x cubed equals to x cubed plus 3x. Okay, so now let's compare the like terms. Okay, so here we have 4 constants, a, b, c, d. So we expect to have 4 equations to solve 4 constants. Okay, good that I have enough color here. Alright, so let's look at the constant term. What a constant term? 2c, 2b, 3a. That's on the left, right? On the right hand side, we can see here, the right hand side, we don't have any constant term, so that equals to 0. So far so good, everybody. And then let's look at the x term. Okay, so we have this guy, so 60, 4c, 3b, and that's it for the left. On the right, we have 3. Okay, let's continue. How about the square term? 60, 3c. That's it for the left. And the right, we have nothing, so 0. And the last we have, which color? I haven't used. Okay, x cubed. X cubed, we have 3d equals to 1. Right, everybody? Okay, let's solve it. Well, here we get d equals to 1 over 3. And then let's go back. So plug it here. So then c, what is c? Well, 3c is minus 6d. C is minus 2d. So when we plug it in here, so we get c is negative 2 over 3. So far so good, everybody? Okay, let's continue to plug in the... Okay, let's plug in... We continue and plug in here. So that is 60 equals 3 minus 4c minus 3b. So 4c is negative become positive. 8 over 3. 3b. Oops. I'm solving for b, sorry. So 3b is 3 minus 4c minus 60. Okay, 60d is 1/3, so minus 2. Okay, so 3 minus 2 is 1. 1 plus 8 over 3 is 11 over 3, right? So b divided both sides by 3, 11 over 9. So far so good, everybody? Okay, then we plug in we plug in a constant term. Okay, so you can see the order. Maybe it's good to compare the highest power term and then the second and then the first power and the constant term. In that order, we can have more space. So we are looking for a. So 3a is minus 2c minus 2b. Minus 2c becomes negative positive. And then 4 over 3. 2b is 22 over 9. So we take the common denominator, which is 9. The first term, we multiply by 3 on the top. 12 minus 22 is negative 10. So a is negative 10 over 27. All right, everybody. So, okay. Let's see. All right. So, what do we get? So, this is our YP. So, YP equals to A. A is negative 10 over 27. Plus B. B is 11 over 9x. Plus C. C is negative 2 over 3x squared. D. D is 1 over 3x cubed. So finally, our solution is the homogeneous solution plus the particular solution. So y of x is the homogeneous solution plus the particular solution. Oops. So that's negative 10 over 27 plus 11 over 9x minus 2 over 3x squared plus 1 over 3x cubed. Okay, so this is what we get for this problem. Yeah, it is quite long. Okay, let's continue. Okay, so actually what we have been doing, the examples are a straightforward case. What if the method fails? Okay, let's look at this example. So let's follow the same things. First step, we consider the homogeneous differential equation. Okay, the characteristic equation is r squared minus 5r plus 6 is 0. Can we factor it? Yeah, how can we factor it? Well, r minus 3 and minus 2, right? So we have r is 3 and r is 2. So what is the homogeneous solution? So 3 corresponds to c to the 3x. 2 corresponds to e to the 2x. So that is our homogeneous solution. Okay, so second step, when we want to find YP, we look at our right-hand side. Okay, so we look at our right-hand side. This guy corresponds to, so this guy corresponds to r equals to 3, right? And what's the general form for it? It should be a e to the 3x, right, everybody? So what happened? Okay, and then we, like what we did, we compute y prime, which is 3a e to the 3x, and we compute y prime prime, which is 9a e to the 3x, and then we plug in the differential equation, and then we get y prime prime 9a e to the 3x minus 5 y prime 3a e to the 3x plus 6y 6a e to the 3x. That equals e to the 3x. Okay, now let's see what happened. Compare the coefficients. We have 9a minus 15a plus 6a equals to 1. Oh, what happened? 9a, 6a, that's 15a. We get 0 equals to 1. Oh, that's impossible. So our method fails. So what happened? Why our method failed? Okay, so let me use, do you like green? Okay, so if you can look back to our, homogeneous equation, do you see this part? So e to the 3x is actually in the homogeneous solution. That means, okay, so it's in the homogeneous solution. That means when we plug in the differential equation, okay, or the ordinary differential equation, we will get when we plug it in, we'll get 0. Okay, and this is what happens. See, you get 0 when you plug it in because it's in the homogeneous solution. So what happened? Well, because you see the 3 is already a root in the characteristic equation of the homogeneous differential equation. So here, then if it's correspond to 3 again, it's like a repeated root. If it's like a repeated root, instead of setting up as like a equals e to the, so this is the wrong setup. Instead of setting up like this, our new yp should be, because it's repeated, so you need to include, you need to multiply by extra x. So this is our correct setup. Okay? Yes. So when you see that the roots that will correspond to, it already appeared in the homogeneous part, homogeneous differential equation. Okay, then you need to multiply your all set up by appropriate power of x. Okay, everybody. So that's why here we multiply by x. Okay. All right. So the theory is your new yp is your OYP multiplied by x to the k minus 1. What's k? Well, k is the multiplicity of the root r in the characteristic equation. Okay, so the multiplicity of r in our characteristic equation is 1. Okay. So this should be 1. Yes. Because now we have an r here, the roots, and there's another here. So together is like multiplicity 2. But if we're just looking at the multiplicity of 3 in the original characteristic equation of the homogeneous part, this is only 1. Okay. Okay, so you multiply by x to the power of k, where k is the multiplicity of the roots in the characteristic equation. Okay, so let's continue. So let's see. Here we have. Okay, to continue, yp prime is, because it's products, so we use product rule. The derivative of the first guy is a e to the 3x plus ax, derivative of the second guy, which is 3 e to the 3x. Okay, and then yp prime prime. Let me write this look better. So I put 3ax e to the 3x. Okay, yp prime prime. Yp prime prime is the first guy we differentiate. Okay. It's so sensitive to my hand. Sometimes I touch it by accident. Okay, where am I? Alright, here. Okay. Okay, so yp prime is 3a e to the 3x. And then there we have the product rule. The derivative of the first guy, which is 3a e to the 3x. And then the derivative of the second guy is another 3 e to the 3x. Okay, let's combine them. So we have 6a e to the 3x plus 9ax e to the 3x. So far, so good, everybody? Okay, so we can then plug in our ODE. So our ODE y prime prime minus 5y prime plus 6y. So y prime prime, which is this guy. So 6a e to the 3x plus 9ax e to the 3x minus 5 y prime is a e to the 3x plus 3ax e to the 3x. Okay, and plus 6 y. So 6y. Y is ax e to the 3x. So far, so good, everybody? That equals to e to the 3x. Okay, let's multiply out. So we multiply out, we get 6a e to the 3x, 9ax e to the 3x, minus 5a e to the 3x, minus 3 times 5, 15. ax e to the 3x plus 6ax e to the 3x equals to e to the 3x. So let's look at the coefficients of x e to the 3x. Then we have, let's see, what colors use, okay, blue. So what is this? We have this guy, 9a, this guy, minus 15, and this guy. Okay, and then on the right hand side we have no, so 0. Is that true? Yes, this is always true. And then let's look at the terms. Did I use this color before? Oh, no? Okay, good. So we look at the terms e to the 3x, and they are this guy, and that's it, right? And then on the right hand side, this guy. 6a minus 5a. Oh, it's a. So a equals to 1. So far, so good, everybody? So a equals to 1. And then, finally, our solution is the homogeneous solution. I touch it again. Okay, the homogeneous solution equals to c1 e to the 3x, and then plus c2 e to the 2x, plus the particular solution. A is 1, so x e to the 3x. Okay, everybody? So keep in mind, we first do our old setup, and then we look at the roots it corresponds to. Do you see the same roots in the characteristic equation? If yes, then you need to multiply your old setup yp by appropriate power of x. And what is the appropriate power? It's x to the multiplicity of the corresponding roots in the characteristic equation. All right. Okay. Oh, yeah. I also put a summary of techniques. Try the solution with the same form. If it does not work, multiply by the appropriate power of x. And yes, we multiply by the x to the multiplicity of the corresponding roots in the characteristic equation. Okay. Let's continue. So, example 5. Example 5. We want to find the general solution of this differential equation. Okay, let's continue. So we do. So first, we look at the homogeneous differential equation. And what is the characteristic equation? Well, that's r squared plus 4r plus 4 equal to 0. And then we have r plus 4, this is a complete square, so r plus 2 squared equal to 0. So r equals to minus 2, because it's repeated, so its multiplicity is 2. Then what is the homogeneous solution? c1 e to the negative 2x plus c2x e to the negative 2x. So far, so good, everybody? That is step 1. So step 2, we want to find yp, and then first, we're gonna look at the right-hand side. Okay, the right-hand side, e to the minus 2, that corresponds to what? That corresponds to r equals to negative 2. So our O setup should be, so O setup means we only look at the right-hand side, okay? It corresponds to negative 2, so that's a e to the negative 2x. So O setup means only look at f of x, which is the right-hand side of the differential equation. Okay, so after the old setup, what? There's an old setup and there's a new setup as well, right? So you realize, oops, -2 is also a root of the characteristic equation of the homogeneous differential equation, right? So that's why you see this term is already in the homogeneous solution. So when you take the derivative and plug it in, you should get the equation is 0. Okay, so that's why we need to increase the power of x. So what is the new yp? Is the old yp. You multiply by x to the multiplicity of the corresponding roots in the characteristic equation, which is 2, right, everybody? Okay, let me use like a different color to indicate the 2. The 2 is here. Okay. All right, so this is our setup. So when you do this new setup, you also look at the root of the characteristic equation and also look at the multiplicity as well, because the multiplicity decides what's the power of x you want to multiply with. Okay, so that's our new p. Then we can continue. So yp prime is, well, you can think of this as like a product. We can use product rule. By the way, you can put like ax squared times e to the minus 2x. Is the same. Okay, so the first guy prime is minus 2a e to the negative 2x times x squared, and then the derivative of the second guy. So a e to the negative 2x times 2x. So let's rewrite it. So it's negative 2a. Let me put the x in front. E to the negative 2x plus 2ax e to the negative 2x. Okay, that's yp prime. Okay, we also need yp prime prime. What's yp prime prime? That is, well, we're going to differentiate, right? So it's a product rule. Again, the derivative of the first guy is negative 4ax times the second guy. And then we have the first guy times the derivative of the second guy. So far, so good. And then plus, here we have another product rule. For derivative of the first guy is 2a. And then times second guy plus 2a times the derivative of the second guy, which is negative 2 e to the negative 2x. Let's continue to plug it into our differential equation. So let's simplify first. The highest power, negative 2 times negative 2 is 4a x squared e to the negative 2x. And here we have negative 4a, there we have negative 4a, so negative 8a e to the, x e to the negative 2x. And then we have the 2a e to the negative 2x. Okay, so let's see. We plug in, and what do we get? So we plug in our y prime prime plus 4y prime plus 4y. Okay, y prime prime 4a x squared e to the negative 2x minus 8ax e to the negative 2x plus 2a e to the negative 2x. That equals to, that plus 4 times y prime. Y prime is negative 2ax squared e to the negative 2x plus 2ax e to the negative 2x plus 4y. 4y is 4ax squared e to the negative 2x equals to, what's the right hand side? E to the negative 2x. e to the negative 2x. Okay, let's multiply out. So 4ax squared e to the negative 2x minus 8ax e to the negative 2x plus 2a e to the negative 2x. Distribute it. So 4 times 2 is 8ax squared e to the negative 2x. 4 times 2, 8ax e to the negative 2x plus 4ax squared e to the negative 2x equals to e to the negative 2x. Okay? Alright, now let's see what happened. We compare the like terms. Okay, for the like terms, highest power terms, x squared e to the negative 2x. We have 4a and 8a and 4a, and is that 0? Yes. Okay, so how about the next term? Oh, let me use another color for that. X e to the negative 2x. So that is this guy and this guy. And then the right hand side we have 0. And this is always true, right? Okay, and then it makes sense because we only have one constant, a, right? So we only need one equation to solve. So that's why the other two equations, we just get 0 equal to 0. Okay, and then we have e to the negative 2x. So we have the 2a, equals to 1. So a is 1/2. So finally, we get a is 1/2. What is our final answer? Our final answer is the homogeneous solution. Okay, c1 e to the minus 2x plus c2x e to the minus 2x plus our particular solution, which is a is 1/2. And then x squared e to the negative 2x. So this is our final answer of this problem. And you can see this is like x squared e to the negative 2x. So it's not appear in the homogeneous solutions. Because if it's the same power, it's already in the homogeneous solution, then the C2 can absorb that term. So it means that like the particular solution is 0. But in this case, it's not the same term. So that's why it makes sense. Okay? Alright, let's continue the rest of the problems in part B, video part B. Okay, see you soon.